Let's do 2 more examples for this part of the video. All right, just make sure it's still good. Everything's still good. And let's see. All right, so for the next example, let's find the relative extrema of f of x, where f of x will be x to the 4th minus 4x cubed minus 8x squared plus 64. Yeah, let's do that. All right. So let's find the relative extrema of this function with a degree of 4. So again, first step, gotta find that first derivative, f prime of x. So the first derivative of this function, so this is just another polynomial. You take the derivative of each individual term to give us 4x to the 3rd minus 12x. 12x squared minus 16x. All right, so here we have our first derivative. So now the second step, set that first derivative equal to 0. So we're gonna have 4x squared, it'll be 4x cubed, not squared, 4x cubed minus 12x squared minus 16x, set equal to 0, and then we wanna solve for x. But before we start solving for x, let's see if we can take out any common factors. Look at what we have here, 4, negative 12, negative 16. What do 4, 12, and 16 have in common? A factor of 4, so we can take out a 4. But anything else, these three terms have in common. A factor of x as well. So not only can we factor out 4 from each of these 3 terms, we can also pull out one factor of x. So you're gonna have 4x on the outside. And if we pull out a 4x from each term, then we're gonna be left with x squared minus 3x minus 4 on the inside, a quadratic instead of a cubic now. So now let's factor out this quadratic function to give us 4x times x minus 4 times x plus 1 equal to 0. And now it's time to solve for our zeros here. By once again setting each factor involving x equal to 0, which means also setting the outside here equal to 0, because we have an x attached to the 4 on the outside. In the previous example, there was no x attached to 3, so we didn't have to worry about that. But in this case, since we have an x attached to 4, then we also have to set that equal to 0. So here we're gonna have 3 equations to solve for. For x equal to 0, x minus 4 equal to 0, and x plus 1 equal to 0. And solving for these 3 equations, we get that our zeros of the first derivative are going to be 0, 4, and negative 1. So here we have found 3 critical numbers. Okay, 0, 4, and negative 1, 3 critical values. Okay, so now that we have found the critical points, now that we have found the points where the slope of our function becomes 0, let's use that first derivative test to determine where we might have some relative extrema. The first derivative test. Again, for this first derivative test, let's first draw a number line and draw our 3 critical numbers first. Okay, so let me draw a number line, a bit longer. So we have 3 points now, our 3 critical numbers in ascending order. We're negative 1, 0, and then 4. Again, since we got these 3 critical numbers, by setting our first derivative as 0, then that means if we plug these values back into our first derivative, it's going to give us 0. All right. So what we want to see is, once again, we want to identify the type of slope, the behavior of original function before, between, and after our critical numbers. Okay, so once again, pick any test points, pick any numbers before, pick any numbers before, between, and then after your last critical numbers. So let's say -2. Let's do, what do we want to do here? Let's do -0.5. Let's do 1 for this one, and then 5 for this last test point. And again, we're going to be taking these test points and plugging them in to the first derivative. All right, so f prime at -2, f prime at -0.5, f prime at 1, and f prime at 5. All right, so let's see what type of behavior, what type of slope our function had before these critical numbers. All right, so again, we're going to take -2 and plug that into the first derivative here. So 4 times -2 cubed minus 12 times -2 squared minus 16 times -2 to give us, if we value that correctly, or like we have done before, you can set up this equation in your calculators and just evaluate and just plug in these numbers. So -2, we should get pretty small slope here of -48. Okay, and -0.5, we get positive 4.5. At +1, we got -24. And if we value the first derivative +5, we get 120. Okay, so pretty big absolute values of slope here. All right, so let's see. What are these slope values? What are these test values telling us about the behavior of our function here? Well, so before our function hits this first critical number at -1, since we got a negative value for the first derivative here, that means our function had negative slope before it zeroed out. Meaning our function was decreasing before it reached that first critical number. Okay. And then after it hit that critical number, after it zeroed out, since our test point resulted in a positive value, that means our function had a positive slope after this first critical number before it zeroed out again. So meaning our function was increasing after -1 and then flattened out at 0 again. Okay. And after flattening out for a second time, since this test point at 1 gives a negative value, that means our function started to decrease again. So it came down, reached that third critical number, flattened out for the third time. And after that third critical number, since the first derivative gave us a positive slope, that means once again, a function was increasing. Okay, so what do we see here? Well, before the first critical number, our function was decreasing and then started to increase after that first critical number. Meaning at -1, since our sign of our slope from negative to positive, that means at this point, we have a relative minimum. So we have relative minimum at x equals -1. All right. And then at that second critical number, since it went from positive to a negative slope, since it went from positive to negative, then that means that second critical value, we have a relative max at x equals 0. All right, but we also have a third critical number. And at that third critical number, before that third critical number, our function was decreasing, but then after it started to increase, meaning our slope went from negative to positive, meaning at this third critical value, we have another relative minimum. So relative minimum at x equals 4, because the sign of our slope went from negative to positive. Okay, so notice that we have two relative minimums and then one relative maximum. All right. So I'll just write it. So first we have our relative maximum here. Our relative maximum was found, or actually, I'm just gonna type it out. Just make it very clear. All right, so again, we have the relative maximum. At x equals 0, and to find the actual value of that maximum point, we have to plug in 0 into the original function, into our original function of f of x. All right, so we plug in 0 into the original function, which again was x to the 4th minus 4x cubed minus 8x squared plus 64. And if we plug in 0 into this original function, we get just 64. So f of 0, our function value of this first critical number gives, or not first, this critical number is 0, gives an output of 64, meaning our relative maximum can be located at the coordinates of 0 and 64 along the curve of our original function. Now for the relative minimum, we had two of them. We have one at x equals -1, and the other at x equals 4. So to find the coordinates, to find the actual values at that minimal point, we're going to plug in these two critical numbers into our original function, so f at -1 and f at +4. And if we plug these in, if we plug these two values correctly, again, into the original function that we have above here, if we evaluate that correctly, we get values of 61 and -64 respectively. So our relative minimum was at -161, and the second relative minimum was at -64. All right, so here we have our relative extremes. Okay, a maximum, relative maximum 0.64, and then two relative minimums at these two coordinates. Again, let's visualize this real quick for this example. So here we have x to the 4th plus 4x cubed. Oh, minus 4x cubed, my bad. Minus 4x cubed minus 8x cubed, and then plus 64. All right, let me set my windows here correctly. Oops, based on our critical numbers. So our smallest critical number is -1. -3 should be good. Second critical number was 5, or the biggest critical number was 5. 8 should be good as well. All right, so now the y values. So let's see. Our relative minimum, the smallest value was -64. The biggest value was +64. So let's make this -70 to +70 for the y limits graph. And here we have our function. Let me make that one a little bit more than -75, +75. All right, so again, starting from the left side here. Oh, dang it, why did I do that? Trace, there we go. All right, so starting from the left side, here our function. It's kind of hard to tell. Oh my God, it's really hard to tell. But let me see if I can zoom in on just that point that I want to show first. All right. Oops, why did that happen here? I put, oh, hold on. Made a mistake. That should be squared, not cubed. I was wondering why it looked like it wasn't going correctly. I don't know what's going on now. All right, Let me double check. X to the fourth minus 4x cubed minus 8x squared plus 64. Now it should be good. All right, so -3, 8, 75. There we go, much better. So again, starting from the left side, our function is coming down, which is the first critical point here at -1 where 0 is out. And at that point, the y value is 61. So here we are relative minimum. Here we have reached a low peak before our function starts to increase, and then reaches another peak here, in this case, a high peak at 0 and 64. So there we reach the second critical value. And after that, it pretty much comes down all the way to the bottom here until it reaches that third critical number. Let's see if we can get it exactly. At 4 and -64. Oops, did I put in the right value? Yeah, 4, -64. So there we have the third critical number, the third critical point where our function zeroes out. And at that third critical point, we have a much slower peak and the first relative minimum. All right, so here we see the behavior of a function based around its rate of change. And we have three critical numbers in which each one resulted in a relative extrema, 2 relative minimums, and then 1 relative maximum. Okay. Let's do one last one here. One more. All right, so one more example. Okay. And for this last example, let's find a relative extrema of f of x, where f of x is -x to the fourth plus 4x cubed minus 20. Okay. Again, first step, find its derivative, find f prime. So first step, find the first derivative of this function, f prime of x, which in our case, derivative of -x to the fourth will be -4x cubed plus derivative of 4x cubed is 12x squared. All right, second step, set this equal to 0. We're going to set f prime of x equal to 0. So -4x cubed plus 12x squared equal to 0. Take on some common factors between our two terms. Well, what do we have in common here? -4 and 12. So we have 4 and 12 here in common. What do these two coefficients have in common? A 4. Plus notice there's a negative in front of this first term here. If there's a negative in your leading term, factor out that negative sign as well. So let's take out a -4 from these two terms. Now, what else do they have in common? 2 factors of x. Here we have x cubed, here we have x squared, which means we can factor out x squared, 2 factors of x from each term, leaving us with the inside here, leaving us left over with x minus 3. Why minus 3? Because again, we factor out a -4, meaning we took out a negative from this first term, and we took out a negative from the second term, which was positive. So if we factor a negative from this term, it becomes negative, right? -4x squared times x gives us -4x cubed. -4x squared times -3 will give us back positive 12x squared. Set this equal to 0, and now set each factor involving x equal to 0 and solve for x. So you're going to take -4x squared equals 0, and then x minus 3 equals 0. Solve for x in each case to give us 0 and positive 3. So 2 critical numbers in this case. All right, and then now the first derivative test. All right, so again, for the first derivative test, we start to solve by drawing a number line with our 2 critical numbers drawn onto it first. All right, so here we have 0, here we have 3. Pick and again, If we to plug in, if we were to plug back these two critical numbers from the first derivatives, it will give us 0, because there's zeros from the first derivative that we solved for. So let's pick any test points before, between, and after our critical values. So let's do -1. Let's do +1 between 0 and 3, and then 4 here. And again, I'm going to take these test points and plug into the first derivative. Not your original function, the first derivative. Okay, which again was -x to the 4th plus 4x cubed minus 20. And if we plug in these three values correctly into the first, again, this is the original function. We're going to evaluate these in the first derivative, which is just -4x cubed plus 12x squared. Right, so if we plug in -1 correctly, if we plug in +1, +4 correctly into the first derivative, it should give us values here of 16, 8, and -64. All right, so let's see what these test points are telling us about our function of x. So based on this first derivative test, since we have a positive slope before this first critical number, that means our function is increasing So our function is increasing before that first critical point at 0, flattens out, but then what happens? The slope is still positive even after that first critical number, meaning our function continues to increase, meaning there is no change of direction around this first critical number. Okay. So our function continues to increase even after that first critical number. But then it flattens out at x equals 3. And in this case, after the second critical number, since the slope is negative now, that means our function comes down. Okay? So what happens here? Well, before the first critical number, since we had a positive slope, our function was increasing. Then it zeroed out, it flattened out, but even after it flattened out, it continued to increase. Meaning, since there's no sign in the direction of our slope, since there's no sign, no change of behavior in our function, that means at 0 here, we have no relative max nor relative min. There's no relative extrema. What we have here instead is known as a saddle point. So we have a saddle point at x equals 0, meaning we have no relative extrema at that point. Okay. But then at the second critical number, we do have a change of direction. Before 3 is positive, after 3, the slope becomes negative, and our function starts to decrease. So here we have a relative. What type do we have when it goes from positive to negative? A relative max. So we have relative maximum point at x equals 3. Okay, so at x equals 0, we have a saddle point, meaning we have neither a max nor a min. Okay, not every critical number is going to give you a relative extrema. So in this case, for this function of x of negative x to the 4th plus 4x cubed minus 20, we only have one relative extrema, and that's a relative maximum. All right, so we have relative maximum at x equals 3, and if we plug in 3 into the original function, again, to the original function of negative x to the 4th plus 4x cubed minus 20, if we plug in 3 into the original function, we get an output of just 7. So relative maximum is at 3, 7. And in this case, we have no relative minimum. Instead, what we found at x equals 0 was a saddle point, meaning neither max nor min. And our saddle point was at x equals 0. And if we plug this into the original function, we get negative 20. All right, so we have a saddle point at 0, negative 22. Okay. Again, not every critical number will give you a relative extrema. Let's visualize this one here. Okay, so what do we have? We have negative x to the 4th plus 4x cubed, and then minus 20. All right, then for the window, let's see, 0 and 3 were our critical numbers. I'll do negative 5 and 8. That should be good. And then our y values, our relative maximum was at 7. And then our saddle point was at 0, negative 20. So let me do negative 25 to 10 for the y limits and graph. So here we have our functions again. Oops. So starting from the left side, our function is increasing, reaches a critical value at 0, negative 20, but that critical value is not a max or min, because even after that critical point, our function still continues to increase. So our function continues to go up until it reaches this very high point here, or relatively speaking, reaches this high point at 3.7, and then starts to come down after the second critical number. So 0, negative 20, we have a saddle point because there's no change in direction, no change in behavior of our function. And then at 3.7, there we have a relative maximum because our function changes from increasing to a decreasing behavior. All right. So that will conclude this part of the video. And we still have a couple more examples to do here pertaining to these first derivatives. We've done polynomials so far, but let's see what happens when we have rational expressions. All right, so in the next video, more examples.